Hi Year 12s, welcome to the final video in the series on circular functions. We're going to go through the test that was given in the final week of term 1, and I'm just going to solve the questions and think out loud. Hopefully you'll find this useful, and after this I may record additional videos, but I need to take a break for a little while because I've spent the whole day recording videos, so it might not be until next week. Some ideas I have are to record a video on pseudocode and also a video going through the 2023 exam papers which were given out in class. So keep a lookout for that. Of course, you're welcome to email me at any time throughout the year with suggestions as well. If you want something, just let me know and I'll see what I can do. Alright, so let's get underway. So we'll start off with the year 11 stuff. So question 1 asks you to label the opposite, adjacent, and hypotenuse sides. So hypotenuse is opposite the right angle. It's facing outwards. The opposite side faces outwards from the reference angle theta. And the adjacent side is the other side, which is touching the angle, which is not the hypotenuse. And by definition, if you remember the well-known acronym SOHCAHTOA, our definitions in terms of O, A, and H are sine equals O over H, cosine equals A over H, and tan equals O over A. All right, that's question 1. Question 2 asks you to draw the triangles from which you can deduce the exact values. So the easier triangle involves an isosceles right-angled triangle with angles pi on 4 and side lengths 1 and 1, giving me a hypotenuse of root 2. From this triangle, I can deduce that cosine of pi on 4 is 1 on root 2. You don't need to write this, but I'm just writing this for completeness and for your reference. Sine and cosine is 1 on root 2. Tan gives me 1. And then the approach was to consider a equilateral triangle with side lengths of 2, which is split in half down the middle to give me a side length of 1. 60-degree angles are pi on 3. Split that in half to get pi on 6. And then this length here, where the triangle is split in half, is root 3. And based on this triangle, we can say that cosine of pi on 6 is root 3 on 2. Sine of pi on 6 is a half. Tan of pi on 6 is 1 on root 3. Cosine of pi on 3 is a half. Sine of pi on 3 is root 3 on 2. And tan of pi on 3 was root 3. I only expected you to draw the triangles. I didn't expect you to write down these exact values, but it's there for your reference. Okay, let's keep going. Question 3. Sine of 3 pi on 2. If I draw a unit circle and make an angle of 3 pi on 2 radians to reach this point here, this coordinate has points 0, negative 1, which by definition is the cosine of 3 pi on 2 and the sine of 3 pi on 2. I'll just move this over because it's probably blocked by my face. Okay, and the y value gives me sine. So here, sine of 3 pi on 2 is negative 1. Now, cosine of negative 75 pi is the same as cosine of negative pi, because what I've done is I've added 2 pi times 37. I'm allowed to circle around the unit circle as many times as I like by multiples of 2 pi. So it's cosine of negative pi. And it's also cosine of positive pi as well if I go around one more time. Now, if I consider this point on the unit circle, negative pi corresponds to this point here, which is -1, 0. And since cosine gives me the x value, this has to be -1. So both answers to part A and part B are -1. All right, question 4. Here we are given a special angle. We don't know what it is because 3 on 4 is not on our list of exact values. But I've told you that the sine of the angle is 3/4, and importantly, this is in quadrant 2. Which means when I find cosine of theta, as asked for in the question, I'm expecting the answer to be negative. So what do we want to do here? Well, what we want to do is use the Pythagorean identity, which states that sine squared plus cosine squared of any angle gives me 1. Cosine squared of theta is going to be 1 minus 3/4 all squared. And cosine of theta is going to be negative since it's in the second quadrant. So that means cosine of theta is going to be the negative square root of 1 minus 9 on 16, which is 1 minus, I should say 7 on 16. So it's negative root 7 divided by 4. Okay, tan theta, by definition, is sine theta over cosine theta. So it's 3/4 divided by negative root 7 on 4. And so that equals -3 on root 7. I'll accept that. Or you can choose to rationalize the denominator as well by multiplying by root 7 on 7. Root 7 on root 7. Okay, both are acceptable. Okay, question 5. If I, for sake of argument, assume that theta is in the first quadrant, theta plus 3 pi on 2 is in the fourth quadrant. Now, if I add pi on 2, or 3 pi on 2, the cosine changes to a sine. So we established that cosine is positive in the fourth quadrant. So that means the cosine will change to a sine, and it's going to be positive. So it's just sine theta. If you're not sure how I got this, you need to review symmetry properties. If you are rusty on this. All right, question 6. You probably wouldn't be asked a question like this on the exam because it's a bit vague. But essentially, all I wanted you to say was no solutions because sine of x is between -1 and 1 for all x. As soon as I go outside this range, the equation has no solutions. Okay, now we're on to exam-style questions. I should say that as I do these questions, it's possible that I'll make a mistake. If you think I've made a mistake, what I'd like you to do is just check on your CAS calculator and just comment on the video, and I can make a correction in the comments section. So here we go. First thing I'm noticing is that we've got sine and we've got minus root 3 on 2. So our basic angle is going to be the inverse sine of negative root 3 on 2, and that is going to be negative pi on 3. Okay, so that gives me my angle in quadrant 4. Sine is also positive in the third quadrant, which is third sine is also negative in the third quadrant, so that would give me negative 2 pi on 3. Okay. This will work. So what we'll do is we'll say that x equals negative pi on 3 plus 2n pi, or, sorry, not x, 3 bracket x minus pi on 3, because I'm solving for theta at this stage, the argument of the sine function. So negative pi on 3, that's quadrant 4, or negative 2 pi on 3, which is quadrant 3. All right, now what I can do is I can divide everything by 3. So that gives me negative pi on 9 plus 2n pi on 3, and negative 2 pi on 9 plus 2n pi on 3. And now I can add pi on 3 to both sides. So this is going to be minus 1 on 9 plus 3 on 9, which is 2 pi on 9 plus 2n pi on 3. And then pi on 9 plus 2n pi on 3. Okay, so now in the domain, so what we'll need to do is start with the solutions that we've got and keep adding multiples of 2 pi on 3 until we exhaust everything in the domain. So the obvious solutions are pi on 9 and 2 pi on 9. And what I'm seeing is that if I go back 2 pi on 3, I've gone negative, I've gone outside my domain 0 to 2 pi. So the only solutions I will get from this point onwards will be found by adding 2 pi on 3 or 6 pi on 9. So 1 plus 6 is 7, 2 plus 6 is 8. I'm still below 2 pi, so I need to keep going. So add another 6 pi on 9 to give me 13 and 14. And those are my solutions. Now, the period is 2 pi on 3, because my coefficient of x is 3. And this domain has length 2 pi. So I'm expecting I'm going to expect 6 solutions, because there will be 2 solutions every period unless I am at negative 1, 0, or 1. So if you recognize that beforehand, you would have known that we would get 6 solutions. Notice that if I add 6 pi on 9 again to 13 pi on 9, I get to 19 pi on 9, which is larger than 2 pi. Okay, question 8. Now this question looks a bit strange because normally we say sine of an angle equals some number or cosine of an angle equals some number. Here I've actually mixed up sine and cosine. So it looks a bit scary. All you need to do is recognize that tan is defined to be sine over cosine. So what I can do here is divide both sides by cosine of 2x and divide both sides by root 3. And now I've gotten back to the equation tan of 2x equals 1 on root 3. And my general solution for tan is the inverse tan of my ratio plus n pi, where n is an integer. So that's going to be pi on 6 plus n pi, or 1 plus 6n divided by 6 times pi. And now I divide everything by 2 to get my general solution, 1 plus 6n pi divided by 12. Okay, we'll keep going. Question 9. Okay, so I think I'll say that the range here will be 1 minus 2 to 1 plus 2, which equals negative 1 to 3. The period will be 2 pi on a half, which is 4 pi. And since this domain is from 0 to 8 pi, I'm expecting to draw 2 cycles. The average value is 1. So now I just need to position some points. So sine of 0 is 0. So at x equals 0, the graph is going to go through 1, the mean. And then at 4 pi, I'll be back to the mean again. Halfway between the start and end of the period at the mean position, I'll have another point through the mean. And halfway between the first two means, I'll get a maximum, and then I'll have a minimum. Okay, so there's our graph. This is very hard to do on a tablet, so I'm just going to make do with the rough graph that I can draw by hand here. It's turning out all right. Okay, we want endpoints labeled with their coordinates, and we want axis intercepts labeled with their coordinates as well. The axis intercepts are here, where y equals 0, so I'll need to label them. In doing so, I'll probably need to solve a trig equation. There's one here as well. Okay, so let 2 sine of x on 2 plus 1 equals 0. Sine of x on 2 equals -1/2. This time I'm going to do it the long way. So I'm going to say x on 2 is going to be the corresponding angle in the third or fourth quadrant. So we know that sine of pi on 6 is 1/2. So I'm going to have x on 2 equals 7 pi on 6 plus 2n pi, and x on 2 equals 11 pi on 6 plus 2n pi. Sometimes it's easier to use the general solution. Sometimes it's easier to just list out the solutions. Sometimes it's easier to use inverse sine. You'll get a feel for how you want to set out your working. I'm not too prescriptive about this. Sometimes it's easier to combine everything into a fraction. Sometimes it's not. I think in this instance, I think not doing it makes it a bit more transparent. So the first two solutions are going to be x equals 7 pi on 3, 11 pi on 3, and then because my period is 4 pi, I will add 12 pi on 3 to get to 9 pi, 19 pi, and 23 pi on 3. Okay, so this is 7, this is 11, this is 19, and this is 23. And if you compare that with the scale, 2 pi is 6 pi on 3. This is slightly beyond 2 pi. And then 4 pi is 12 pi on 3, and this is slightly before that. So this makes sense. And then all I need to do is add 4 pi to get the next few values. So that looks good to me. All right, question 10. Looks a bit scary because it's a translation, and we know that with cosine, it's not going to be super easy. So I think here it's worth, again, writing down the range. So the range will be from 1 minus 2 to 1 plus 2. So again, -1 to 3. The period will be 2 pi on 3, since the coefficient of x is 3. So now we need to look at the fact that there's been a translation, pi on 3 units to the right. And we know that cosine starts at 0, 1. So this graph will have its first peak at pi on 3, 3, which is the maximum. And then the graph is going to repeat every 2 pi on 3 units. So from pi on 3 to 2 pi on 3, I won't get a full cycle, I will get a half cycle, which means the graph is going to do something like this. The reason why I know I have a point here is because I will have a position at the mean value halfway between the minimum and the maximum. And similarly, I will get this happening. Okay, and now I can join the dots. Sorry that it's sloppy, but this is a tablet. It's quite hard to do this. But that looks pretty good. So 1, 2, and my domain has 2 cycles of length 2 pi on 3, so this is what I'm expecting. Okay. I'm just going to change. Oh, no, I can leave that there. That's the maximum. Now we want to label the endpoints and the axis intercepts. So -2 pi on 3, -1, 2 pi on 3, -1, and the y-intercept is at 0, -1, and then I will have x-intercepts here and here. So again, we'll need to solve a trig equation to find the location of these intercepts. So let's go ahead and do that. So our equation is 2 cosine of 3 brackets x minus pi on 3 plus 1, and for an x-intercept, we'll set y equals 0. So cosine of 3x minus pi equals -1/2. Now, if I I'll just do it. So 3x minus pi, well, the inverse cosine of +1/2 is pi on 3. So my first angle is going to be 2 pi on 3 in the second quadrant and 4 pi on 3 in the third quadrant. And now we take away, now we add pi to both sides. And now we divide everything by 3. So 5 pi on 9 plus 2n pi on 3, 7 pi on 9 plus 2n pi on 3. Okay, so where is 5 pi on 9? Well, that is just before 6 pi on 9. So this point here is going to be 5 pi on 9. And if I take away 2 pi on 3 to get from this point to this point, if I subtract 6 pi on 9, I get -pi on 9. Seven pi on 9 lies outside my domain, so I'll need to take away 6 pi on 9 twice. So 7 pi on 9 minus 6 pi on 9 is pi on 9, and pi on 9 minus 6 pi on 9 is -5 pi on 9. And you'll notice that these solutions are mirror images of each other, and that's because the graph is symmetric about the line x equals 0. So it's worked out. It's what we expected to happen. Now, don't forget to label the y-intercept. I forgot to do that when I did this test earlier. Okay, so that's how you do this question. It's not too bad, but you got to be pretty efficient when dealing with circular functions because you don't have a lot of time in exam 1. You're really expected to be able to sketch these graphs and solve these trig equations as confidently as you would with an exponential equation or a quadratic equation. Okay, for question 11, there are going to be many possible solutions. I'll I'll leave it to you to work out whether your solution is equivalent. I'm going to write down the most compact solution. So sine x equals a half. The inverse sine of a half is pi on 6. So all we want to do is have negative 1 to the power of n times the inverse sine of the ratio plus n pi, where n is an integer. You need to write this part, otherwise you have not stated a complete general solution, because you need to specify the meaning of the parameter n. All right, for cosine, here what we want to do is say 2n pi plus or minus the inverse cosine of a half, which is pi on 3. For tan, it's the inverse tan of the ratio, which is pi on 4. And since tan has period pi rather than 2 pi, we can just say it's n pi. Again, where n is an integer. Now, equivalent solutions would include pi on 6 plus 2n pi, 5 pi on 6 plus 2n pi. So this separates out the first and second quadrant solutions. For part B, you could have pi on 3 plus 2n pi, negative pi on 3, or 5 pi on 3 if you chose a positive angle, plus 2n pi, where n is an integer. And for part C, I really do want you to write this one, but if you happen to write pi on 4 plus 2n pi for quadrant 1, and 5 pi on 4 plus 2n pi for quadrant 3, that is a correct solution, and so I would choose to award marks for that, and I hope VCAB would as well. Okay, question 12. What we want to do here is perform a quadratic substitution with cosine of x. So what we have is 2u squared plus 3u plus 1 equals 0, where u equals cosine of x. And here we can make the substitution, the factorization, 2u plus 1, u plus 1, noting that 2u times 1 gives me 2u, 1 times u gives me u, and 2u plus u gives me 3u. So u equals negative a half, or u equals negative 1. Now this question says find all solutions, which means we're after the general solution. Okay, so now we can go back to cosine. So cosine of x equals negative a half, or cosine x equals negative 1. So we have two trig equations to solve here. The inverse cosine of negative a half is 2 pi on 3, remembering that inverse cosine is between 0 and pi. So we're going to write x equals 2n pi plus or minus 2 pi on 3, where n is an integer, for the first family of solutions. And then for cosine of x equals negative 1, here there's only one value in the interval 0 to 2 pi that gives me a value of negative 1, and that is pi. And then I can add 2n pi as well. Now, you might have chosen a different angle to 2 pi on 3. That's fine, as long as your solution is equivalent. So if you have a different answer here, just check that you generate the same families of solutions, and I would give you the mark for that. Some people would choose to group everything together. You don't have to. If you wanted to, you could say x equals 6n plus or minus 2 pi divided by 3, since 6 divided by 3 is 2. And 1 plus 2n pi, where n is an integer. Okay, last page. Now, question 13 is quite difficult. I don't think this would be asked on exam 1. I mean, it could be asked, but it'd be a question that would separate most of the students, in the sense that only the top students in the state would be able to answer this question in 2 or 3 minutes. So what's going on here? What we're saying is, suppose I have the cosine graph, and then I have the sine graph, like so. What translation do I need to do to move from sine of x to cosine of x? Well, from this graph, you should see that if I shift pi on 2 to the left, we get to cosine. Okay, so that means we've said that sine of x plus pi on 2 equals cosine of x for all x. Now, this formula should be familiar from your symmetry properties. So if you're rusty on that, look it up again. Now, so clearly, m equals pi on 2 is m equals negative pi on 2 is a solution. But the question doesn't ask for a solution. It asks for all possible values. So not only do we need to translate negative pi on 2, but really, because sine and cosine I'll say, yeah, sine's fine, sine or cosine is fine. Since sine has period 2 pi, m equals negative pi on 2 plus 2n pi, where n is an integer, defines my full set of solutions. Since if I shift over by pi on 2 and then shift by any multiple of 2 pi, I get back to the same graph again. So your final answer is going to be this: negative pi on 2 plus 2n pi, and if you have an equivalent expression, I will accept that as well. That concludes this series on circular functions. Good luck with the homework. And if you think there's an error in this video, please just leave a comment on the YouTube video and I will happily respond to you. Thanks, Year 12s.